what it meant here by concrete members would be concrete slabs, beams, columns, foundation, walls. I mean, this is what we call here concrete structural members, if you like. Here is a picture that shows a building, like a cut through a building. This is where the people is going to be walking, right, and use it. Same thing here for the first floor. And this kind of a pavement. Look here at the grade. This gives you the grade outside the soil, and we're just putting all of this level below the grade. We call this pavement. In this case, give you the first floor, it's give you the second floor. So the floor itself is give you that surface that you walk on and use, correct? This floor is composed of a thin slab. So what is a slab? The slab is give you this piece here, the thing that you're cutting through. We call this concrete slab. In here we have concrete slab, which is this one, and supported over joist. This gonna be like joists running all the way from here to there. It's gonna be running this way, right? And the slab itself is supported by all of these joists. And then these joists are supported by a beam. Look at this beam. This beam is running across to support all of these joists. Let's go here to the first floor. First floor, we have concrete slab. And if you see here, it looks like thicker, right? A little bit thicker, right? And then you have some beams. And you see the beam is running across like this, in this direction. And the slab is supported by beams, not by joists in this case. Meaning that we can have more than one different system. Just depends on the way that you design it. So in this case here, the load goes from the slab. Now the loads could include dead load and live load. Dead load is going to be self-weight of all objects, including self-weight of the structure. And dead load is going to be, this load is going to be staying there. Permanent loads. Like for example, if I'm going to put some flooring, if you put tiles here, it's going to be dead load. If you put a ceiling from the underside of this slab, a floor system, we call this dead load. If you put some ducts and cables, light fixtures, we call this dead load. If you put some equipment, like permanent equipment, like an AC unit, we call this a dead load. But if you put people, furniture, we call this live load. If you put light equipment, anything that you can move around, right? We call this live load. If you put some light partitions, you know, like stud walls, we call this stud walls, light partitions on the top of this concrete slab, we consider it to be live load. These partitions, you can move them at any time. Let's say that you have an office space, here's the office now, and later on you can maybe move this partition, just move it anywhere else. So we consider this to be live load.
The partitions, you mean like kind of like cubicles?
Like cubicles and also like walls. Like the wall, if you think about non-bearing wall.
Oh, okay.
Because we have two types of walls. We have bearing and non-bearing. Bearing, it means that you use it to support other stuff, other structural members and non-structural members. Load bearing is the one that you use it to support it, right? Non-bearing, you're not going to be using to support any loads. So if you think about an office space and then you have some actual walls, not just for cubicles. Cubicles considered to be part of the furniture. So it is all live load. A copy machine is going to be live load, right? Any other light equipment, computers, they're all live load. I know that furniture may stay there for a long time, maybe 10 years, right? Maybe no one's going to change the location. But because you are able to change the location and to change the magnitude, which means the amount of this load, we're going to treat them as live load. So this concrete slab supports dead load and live load. The slab doesn't support the joist. You guys understand that. This beam does not support the slab. The beam supports the slab, but the slab does not support the beam, right? Excuse me if I missaid it. Same thing here for the joist. Joist support the slab, but the slab itself does not support the joist. So when you say dead load for the slab, is going to be the slab weight only. But dead load for the joist is going to be the weight of the slab and the weight of the joist, if this makes sense. Same thing for the beam. Dead load for the slab is going to be the slab weight only. But dead load for this beam is going to be the slab weight and the beam weight. Make sense? Any comments on this? Questions? Okay. How about life load? Life load is going to be furniture and whatever that you put on the top of this level here. So what happens to the load? Load includes dead load and life load. It's going to get supported by the slab, and then the load is going to be moving to the beams, and after it goes to the beam, it's going to go to the column. So this is what you call here the load path. The load moves from the slab to the beam to the column, and then after that, it goes all the way down to the column, to the footing, and then to the soil. This is what you call here the load path. You need to have the good connection here between the slab and the beam, or the joist, and also between the joist and beam to the column. If I look here at this, I'm gonna say, you know what, this footing or whatever foundation that I have for the building supports the entire building. You should agree with me, right? Because eventually all the load is gonna be supported by the soil, so it needs to go through the footing. But how about if I said this column right here at this section, does this support the first floor? See, no. This column, this piece of the column supports the second floor only, and whatever above. This column here support everything above, and this column support everything above. So this column support the first and the second and whatever above. This column support the second and whatever above, right? So if you like to design here the column, this is going to be designed to support everything above. But this column section right here, I understand this is going to be the same column, right? But the column location, when it happens above the first floor, is going to be supported the second and whatever above. How about the wall? What does the wall support? I'm going to say the wall support this brick wall right above it, and also part of this second floor, and then also support everything above, including this. That's going to be going to this wall. Okay. So now we have an idea about the load path, about the type of load. We have dead load, and then we have life load. So you guys shouldn't be confused about this, right? So I'm going to say, how about the stairs? How to support it here in this case? I'm going to say the stairs is like a slab, but it has some steps. And the stairs is supported from the top on a beam that's running in this direction. Most likely, you're going to see a beam running from here to there. And then the bottom is going to be supported by this wall, because you see it goes from here to there. So this is how the stairs is supported. So you really need to have a support, whether you're going to have simply support, like simply supported beam. You can take any structure member and consider it to be simply supported beam, or maybe it's going to be continuous beam. Because if you have continuity, I know that you guys understand what's continuous beam, right? Continuous beam is going to be that beam that goes like this, and then you have few supports. You have a support here, another support here. If you just do it this way, we call this simply supported. You start to add supports in the middle, we call this continuous beam, right? So here's a beam, and then you have more than two supports. Another type of construction, you have just a slab and no beams. You see this? I have no beams at all. We call this flat plate, or you can call it also flat slab. Difference between the two, in a flat plate, you don't have this column caps. You see this column caps, and we call this drop panels. So you see here at the top, at the roof, just clean. You don't have anything. In here, I'm gonna start to put some caps. Also, I'm gonna start to put some drop panels. Why do we have this column caps and drop panels, and why don't we have it here? Because we're concerned here about the connection between the column to the slab, right? One of the failure modes for a slab column connection is going to be called punching shear. And what is that punching shear? Punching shear is going to happen when this column is going to be punching through the slab. This is very similar if you're going to bring here a piece of paper or maybe a napkin, right? And just bring a pen, and then you try to do it this way, right? You're going to see no resistance. The reason because of this punching shear. You have high stresses right below the pen when it comes to the very thin tissue or napkin. Same thing here. If the load that goes to the column is high and this slab is going to be very thin and has no enough strength to resist this punching shear, Just the slab is going to be coming down. It's going to be punching like a round hole around this column. We call this punching shear. Because we are concerned about punching shear in some cases, and of course it has some analysis, you can start to add here and make the column a little bit larger when it meets with the slab. So we call this column cap, or we put this drop pane. So why do we add them here? To protect the column to the slab connection from the punching shear. And of course has some analysis. We don't just put it this way. Now in a case like this, dead load on live load is going to be coming from the slab to the columns directly. There's no beams, and then goes all the way down to the footing. In some cases, we put a beam on the perimeter, but we still call this flat plate or flat slab. Reasons because I don't have beams running between columns. Unlike this case here, you see, usually the load is going to get directly from the slab to the column. It needs first to go through a beam, but here it doesn't go through beams. So we call it flat plate or flat slab. Another 3D picture here that shows what's happening in a reinforced concrete structure. Just look at this. Here's a concrete slab supported by beams. So if you like, you can consider this to be continuous beam. If you like to do your analysis, you're going to say this is your continuous beam. And here's one support, two supports, and here's the third support. So where's your beam here? Your beam is going to be running from here to here. So you do your analysis for the slab itself. You're going to have here three supports. Here's one, which is this beam. Here is two, and here's three. Now I start to connect between structural analysis and statics and between actual structure members. So we can say now the beam is also supported by two columns. When you look at any beam, I'm going to take you back here. Here's a beam supported by a column here and a column on the other side. Here's a beam supported by this column, this column. It may also be continuous, you know. So the beam also, you can take it like this and then start to put the loads on it, and the supports can be the columns. So if you like to design the column, columns can be designed for an axial load. And this axial load is determined based on the reaction. So the axial load on the column is going to be the same as the reaction coming from your beam analysis. Okay, yes, now it makes sense. We call this basement wall. This is going to be concrete slab, right? Beams, you have some columns, then you have some walls. You see the concrete wall here, and then you have some footings, continuous footing. And this is going to be the soil surrounding the foundation. Another nice picture here shows the columns, and this column you're going to be designing for axial loads, because these support here mainly axial load coming from the beam and coming from the slab. And then after that, the force is going to be going to the soil through the footing. So this is going to be what we call here foundation or footing. Foundation is kind of more generic term, but you still can call it here foundation or footing. Both of them is going to be okay. And here's some of the walls, right? Now, this picture here, this illustration shows you here the load path that I was just talking about, but it's more colorful, you know. The load that you have, you're going to have the self weight of the slab, right? Which is the slab load, right? Plus the beam load. Plus what? The surface load. Surface load is most likely is going to be your life load that you put in there. Life load includes what? Includes people, furniture, light equipment, and maybe some partitions. But also you may have part of this surface load is going to be a dead load, like flooring. If you are going to be adding here some tiles, tiles going to be permanent. I mean, you're not going to move it every day, but for furniture, you can move it. You can easily take a desk and just move it around. So this surface load includes dead load on life load. And you see what happened? You put the loads here on the top. Sometimes you have point load. Sometimes you have uniform distributed load. So this point load, it can be like an equipment. Someone's going to say, build the equipment is going to be maybe 2 feet by 2 feet or 3 by 2 or 3 by 4, right? But you can treat it as point load if you want to. This is like simplified way of looking at the loads. You just consider it to be a point load. So your job here, if you're designing the slab, you take this surface load and then you design the slab for it. And then after that, the load is going to be going to the beams. And after it go to the beam itself is going to be supported by the columns. Now the column here is going to be supporting axial load, and then after that, give it to the footing, and from the footing to the soil, which is the ground here. So this picture makes sense, and I mean, it really illustrates the load path here. This is going to be very clear to you that beam is supporting the slab, columns supporting beams, footing supporting columns, and then the soil supporting the whole thing. Any questions?
No.
You're good? All right, great. Now, looking here in the 3D and looking from the underside of the beam system, so I'm gonna have here a concrete slab, which is this piece here. Then I have a couple of beams. Then I have 4 columns. I'm trying to think here, what happened when you put this point load in the middle? What's supporting it? Does it go to the column, or goes to the beam, or goes first to the slab? I'm gonna say first it's gonna be going to the slab. And then this load P is gonna get transferred through this slab strip. So I'm gonna say this is what we call here slab strip, right? Which is this section here. And this slab strip is supported by these 2 beams at 2 points, point B and point C. So the load here P, if this happened right in the middle of the span, half of it is going to be going to B and the other half is going to be going to point C. Now let's look here at what happened afterwards to the force. The force here is going to be coming to point B, which is 1/2 of P, if you like. So I can say here 1/2 is going to be coming this way, right? So the force here at B, if just happened and this P was right in the middle, this force at B is going to be B over 2. It's going to be P over 2, right? 1/2 of it is going to be coming here, and the other half is going to be coming in this side. This also is going to be P over 2. Okay, great. Now, this is here also a beam that takes the load from the slab and then start to support it by this beam, right? So the load is coming here, supported by this beam, and if it happened that this is right in the middle, 1/2 is going to be coming here, the other half is going to be coming to this column, meaning this load at this point is going to become like this, and this is going to be equal to 1/2 of this load, which means P divided by 4. Now let's check the other column. This is going to be also P divided by 4. How about this one? P divided by 4, P divided by 4. So that makes sense. You start by one load P and then you have it divided by 4 because all columns here are supporting it equally. Just because this point load is happening right in the middle. So I'd like to design the slab. I'm going to consider it to be like a beam. So when it comes to structure analysis, I'm going to be modeling this slab as a beam. It's going to be like this, right? This is going to be for the slab now. And then I'm going to have 2 supports. It's going to be like, I'm going to treat as simply supported. Now this is going to be the slab, and this is going to be the beam, and this is going to be the beam. You see this? This is going to be the slab, a beam, and a beam. The 2 supports. So I can come here and then call this to be, this is going to be the slab, right? And the support itself is going to be the beam. Okay, makes sense, simply supported. How about this beam here? How can I model it in structure analysis? I'm going to say, I can do the same. Here's my beam. It has 2 supports. And in this case, the support is going to be a column. So I'm going to come here, I'm going to say, this is here my beam, right? And this is going to be a column. And this is going to be also another column, which is going to be this guy here. So now it makes sense, yeah. What do you call this point here when you have the point load? I'm going to put here the point load is going to be like this, right? What do you call this point? Yeah, do we have a name for it? It says here P, correct? So I can call this to be P. Here's the point P. What point would you call this? I'm going to say this is actually going to be point B, right? This is going to be B, and this is going to be C. C is going to be on the other side, correct? Okay, now this makes sense. Yeah, this point C and this point B, this is going to be for this lab. How about for here? Here's this beam. I have taken only this beam, not the other beam, just one of them, which is this one. So I'm going to say this one here is going to be D, right? and this one here is gonna be E, I guess. It's gonna be like that, right? And this point B is gonna be right in the middle. It's gonna be 1 point here, right? So now I understand what this means by modeling structural member, including what? Including slab, beam, and a column. How about the column? How do you model a column? Well, a column is gonna be a vertical member, right? It's gonna be like this. Has lateral support, like this. Another lateral support, which is a concrete slab and concrete foundation, right? Because this column cannot move right or left on the top. It is supported by something there, which means it has a support like this, right? And also at the bottom, let's say at the foundation, it has also support because it is well connected to the footing, right? And then what? Also, I have a support for it, which is the footing. You remember the footing? The footing now becomes this support. I'm gonna take you back here one slide. Here it is. Here's a column. It has a support in the X and in the Y direction, right? It cannot move right or left. And at the bottom also it cannot move right or left. And also at the bottom, it has a support here, right? The column itself is supported here at this point. The column is not supported at this point, right? It doesn't have any support here. Support is at the bottom. So this is why I put the support here at the bottom. Now, let's start here by putting the point load from here, right? Based on your analysis, you're gonna have this P over 4. How about the force here in this member, in this reaction? Do you have a reaction in this direction? If I put this force here to be P over 4, how about the reaction at the bottom? How much is gonna be?
P over 4.
Yeah, it's the same force. How about this lateral force? Do you have any values for it? You can say no, nothing. It's gonna be 0, 0, and this is gonna be P over 4. Unless you have some lateral forces, like for example, earthquake forces, right? If the building here is gonna be start to shake right and left, you're gonna see here some forces in the column. But for this given loads that I'm talking about, gravity loads, we call this gravity, which means based on the weight, like this, the weight of the dead load, right? And then also you have the life load. You don't have here any seismic forces or any earthquake forces. So I'm not handling here any earthquake forces. I'm just talking about the vertical loads. So in a case like this, you have no reactions here. So out of this 3 slides or 4 slides, right? Now I understand that I have some structural members, including slab, beam, and column. And also I understand here, I learn how to connect between or how to correlate the actual structural members to the structure analysis system that I used to work with. Like a simply supported beam, in some cases maybe continuous beam, if you're gonna have more columns, right? And then even for the column itself, it's gonna be like simply supported structure. But instead of having the loads coming this way, it's gonna be coming from the top. You guys agree? Now we understand the meaning of the structural members that you have studied in structure analysis and between the actual concrete members. Should I assume so and move forward, or any questions?
No questions here.
Okay, great. You guys don't feel shy to ask. This is gonna be your perfect time to ask before you face your midterm, the final. Anyways, this is almost the same structure, right? The same structure here. And then, as you see here, you look at the beam and then you say, where's my beam section? Is my beam section is gonna be stopping here? Is this my beam section? This gave you the question, right? If I may zoom in here. Where's the beam depth? Because in the past, I have seen rectangular section, right? And T-section. Now, where is the rectangular section? Do we have a rectangular section ever? You can say almost no, you don't have. But if you like to simplify your analysis, you can do something like this, you know? So someone can come here and say, you know what? This section, I'm gonna just ignore the slab or the flange. We call this the flange, right? I'm gonna ignore it. I'm gonna treat this section to be my concrete section. It's okay. If someone would like to do it this way, this is an actual practice and design. I'm not talking about an exam or homework. In the homework, I'm gonna be very specific. If this is gonna be a T section or rectangular section. But let's say in reality, how would people treat it? And what is the reason? In certain cases, we just ignore the effect of the flange, the T, and just consider it to be a rectangular section. You say, yeah, you can consider it to be this way if you like. The other question is, should I consider the slab to be part of it, or should I consider it to be this way? You see this? Which one's correct? Is it this option, or the entire thing including the slab? You say, no, in this case, of course, I'm going to be taking it the entire like this, right? This is going to be my rectangular section. If the T is there, if the slab is there, now it's going to be part of this. Why would you cut it down? Right? You just consider the entire depth of the slab. Don't just take it to the drop. Because this is going to be the drop. This is going to be the drop from the concrete slab. But you need to consider the entire depth of the slab. Now, since usually beams have slab on the top, it means you're not going to see a rectangular section. This is going to be a rare condition. It may happen in certain buildings in a certain way. Let's say that you have an opening next to this beam, let's say from both sides. If you have an elevator on this side, also an elevator on this side, you're going to see a rectangular, actual rectangular section, pure 100%. But in most cases, it's going to be a T section or an L section. So we call this L, we call this T. Now the question is, do you really want to treat it to be a T section, or do you want to treat it as a rectangular section? It's going to be a different story that we need to discuss it. But in actual practice, at the beginning, we consider it to be rectangular because it's going to be simpler in analysis, right? You'd like to simplify it. And if you really need the help of the T section, you can go for it if you want to. Meaning, if I have a situation like this, I'm going to put here this situation like a T section. One person would like to analyze it to be a rectangular section. The other person wants to be a T section to consider in his analysis. Which one do you think is going to be getting higher strength? Is going to be the T section or the rectangular section?
The T section.
The T section, right? This is why I say, well, if you like to simplify it, you're going to be going with the rectangular section. But reality, yes.
How long do you know that the T section will be though?
You mean the width of it?
Yeah.
This width? We're gonna, once we get to it, I'm gonna tell you exactly what the code says.
Oh.
The ACI don't just leave us to decide on this width, because someone can take it all the way to here, right? And from this side all the way to here. So there should be some guidelines. The code is very specific in this. Okay? But the bottom line here, and what I want you really to know, that T sections are stronger than a rectangular section. You need to understand this. You need to have this feeling, right? And for simplicity, you can just consider it to be a rectangular section for now, but later on, you can treat it as T section if needed. Okay. Here's a section, and this is going to be the parameters we're going to be using. Like, for example, total depth. We call this total depth of the beam is going to be H. The depth from the compression. Don't forget, here's going to be compression, and here's going to be the tension, right? We call this depth. Where does this depth goes to? This D. You can see this depth, it goes to the center of the rebars. You see this? Let me zoom in. It's going to be right here. So this depth is not to the bottom of the rebars, not the top of the rebars, it's going to be to the center of the rebars. Why? Because this is going to be the centroid of the force. If you have any tension force, it's going to be right here. It's going to be right in the middle of the rebar. So in a case like this, you need to take this depth from the top compression fibers to the middle or the centroid of the reinforced bars. You can say, how about here? When you have 4 bars, where's the centroid of the rebars? I'm going to say it's going to be right in the middle, right? Look at this. Right in the middle of the rebars, the mid-height. This is going to be the centroid of it. How about here? It's going to be this rebars, right? It's going to be like this. So, okay. So what's the difference between the 3 sections that I'm looking here at? This is going to be a pure rectangular section. Depth D, total depth H. So what do you call this? It's going to be beam depth. How about this one? Total depth of the concrete member is going to be called H. How about B? B is going to be the width. Okay, so these 3 parameters, I'm going to keep on using them. Here's H, B, but in this case, you call BW. Why BW? Because of this is going to be the web. W stands for web. How about here? you put the flange at the bottom. Sometimes in precast structures, we do the beam this way for certain detail requirement. And in a case like this, I'm going to call it the width of the flange, BF. Okay. How about this? This is going to be the width. Where's the depth? This is going to be compression. This is going to be the center of the tension. Compression, center of the tension, total depth. Okay, now I understand all of these terms. How about this HF? Sometimes also they call this HF, which means the slab thickness or the thickness of the flange. They call it T sub S. What is T sub S? It's going to be T for the thickness and S is going to be for the slab. TS is also used for slab thickness. So I'm going to say the same for the slab thickness. You can use it, should be fine. What is this AS? AS is going to be total cross-section area of the reinforcing. What does it mean? It means in this case is going to be the addition of the 3 rebar cross-sectional area. Same thing here. It's going to be the total cross-section area of the steel. Same thing here. How about for 1 rebar? I'm wondering if we have seen 1 rebar before. Did we talk about 1 rebar cross-section area for 1 rebar?
Yeah, there's a code for that, right?
Which is this table here, right? So this is going to be the bar size. So for example, we call this number 3. How do we write here number 3? Yes, say we write it like this. We say, for example, number 3 bar. This is the way we write it down, right? Number 3 bar. What is the cross-section area width? For number 3, it's going to be 0.11 square inches. What do you call this? Is this AS? You can say no. This one here, we call it AB, A sub B. What is A sub B? Cross-section area for 1 rebar, A sub B, right? Now let me move to this. Which means in a case like this, if you have the rebars, it's going to be at the bottom, right? And let me assume here for a second that I have 3 number 6 rebars, right? I'd like to do some quick analysis here. What does it mean by a number 6 rebar? How much is the cross-section area for number 6? Can someone help me?
0.44.
0.44 square inches. So I'm going to say, right next to this, I can say A sub B equals 0.44 inches squared, correct? How about AS in this case? How much is going to be? So I have 3 rebars, right? 3 times 0.44. How much is this? Is it 132? Okay, inches squared. Now you have here a quick example how to do the analysis, how do you find out AS? I guess if you have here 4 number 9, I need help. What does it mean by 4 9? How much is AS if I have 4 number 9? Charles, can I ask Charles, please?
Yes, sir.
Yes, my friend. 4 number 9. How much is AS for 4 number 9?
AS for number 9. The bar size number 9?
Yeah, the bar size number 9. How much is AS? First, how much is AB?
AB, I'm not too sure.
Okay, where's AB? Do you see here AB here somewhere?
I see nominal diameter and nominal area.
What is AB?
I'm not too sure.
Okay, thank you. Michelle, you're gonna say something there? How much is AB for number 9? And if I have 4 number 9, how much is AS?
AS is 9 and AB is 1.
Okay, AB is gonna be 1 square inches, and 4 number 9 is gonna be how much for the AS?
4.
It's gonna be 4. Okay, yes. So I guess 2 people say that, right? It's gonna be Michelle and who else? Who said that? Was it Omar?
Oh, I turned on the mic. Angel.
Angel. Okay, thank you, Angel. Thank you very much. Okay, yes, this is correct. So I guess by now you understand what is the use of this AS. How can you figure it out? If I tell you here, this is gonna be the reinforcing you have. Now you know how to find out AB and AS, right? Please stay focused with me. I don't want you guys to miss part of this lecture. because everything is going to be built on the previous information that you just learned, right? So be sure that you don't miss a section of this lecture. Now I'm looking here at this beam, and here's one of the beams, which is this beam here. I'm going to be taking this beam, going to start here to put some loads, right? To start to put some loads on the beam. Now what's going to happen? This is going to be here continuous beam, right? It has some continuity here, or maybe this is a cantilever, It's not just simply supported. It has an overhang like a cantilever, or maybe it's continuous. It's going to be one of the two. When you apply the loads, you're going to see here right in the mid span, you're going to see some deflection. The beam is going to be coming down. It's going to be sagging here. And of course, you're going to be developing some cracks. Meaning, on this side, you're going to have some tension, right? In the top, you're going to have some compression. This is why I don't have cracks here. And you know that concrete is going to crack in tension. This is why I need to have some reinforcing at the bottom to take the tension. But when it comes to the top of the beam, guess what's going to happen? Where's the tension is going to happen? You're going to say tension is going to happen here. And also tension is going to happen here, top of the beam, while compression is going to happen at the bottom of the beam, right? So what do you call this moment here? We call this positive moment. Be positive moment, right? So in here we have positive. What does it mean by positive moment? It means tension is going to be at the bottom. About here, I'm going to call this to be negative moment. And here also, I'm going to have here negative moment. Now, what's the difference between positive moment and negative moment? Positive moment, the tension is going to be at the bottom. Negative moment, tension is going to be at the top. Now, where do we need the reinforcing bars? You say reinforcing bars here is going to be needed at the bottom, right? Of course, it's not going to be straight because we're just exaggerating here in the deflection of the beam, right? So you say reinforcing bars is going to be coming like this. It's going to be going through the entire thing. Or if you like, I can just draw it like a broken line, right? But in reality, it's going to be straight line because deflection is not going to be that excessive. You guys know that deflection is going to be that much. We're just exaggerating here. This is going to be the tension rebar at the bottom for the positive moment. In the top, I will need here the tension rebar for the negative moment to be in here. It's going to be like that. Then I need to stop it here somewhere. I don't really need to extend the main bars throughout. Just need it whenever I have the big tension force here in the beam, if you like. And I put it like this. Of course, it's going to be one continuous rebar, right? This is where you put the tension rebars. Just something came here to my mind that whenever you do any analysis, any calculations, just my advice to you guys, especially when it comes to multiplication, right? Put like an X. But if you like, you can put a star. Right? You can do this if you want to. Or you can put X. What is danger about using point? Like, for example, I'm going to say 4.4 equals, for example, 4. Does it make sense? 4 times 4 is equal to what? You're going to say here 16 inch, correct? There's going to be 4 times 4. But someone's going to be looking at this equation later on and says, are you saying that 4.4 equals 16? What's wrong? So please do either star or do X. Just avoid this mistake because you may just lose point for something very simple. I mean, nothing wrong if you do this. I mean, this is what we have learned in school, right? But just to make yourself clear, either this or you can use this. Just an advice. Now let's look here at the 3 sections. Let's cut here section through the middle of the span. Now where's the tension? Tension is given at the bottom. Compression at the top. Here's our section. This is a T section because I'm going to have a flange. And here is the compression. Here's the compression I'm going to be hatching it. Now, do you know if the compression is going to be within the flange only? Or the compression may be extended like in this case? Look at the difference between this and this. What happened here? Your neutral axis is going to be within the flange itself. You see, this is going to be the neutral axis, right? But here the neutral axis just happened to be in the web. So, okay. How about here the neutral axis for this section BB? Yes, it's going to be right here. Now, where is the compression? Compression is going to be at the bottom, and this is going to be the tension reinforcement. This is going to be the tension reinforcement. This also is going to be the tension reinforcement at section AA. So what's the difference between the three sections again? This one here, section AA, positive moment. This one's going to be negative moment. Compression is going to be at the bottom. This one, it is going to be positive moment, but different scenario. So again, when you do your analysis, you're going to end up with a beam. It could be like this for the positive moment, or it could be like this. Which one do you think is going to be simpler in your analysis? Which one do you think is going to be needing less equation? This case or this case? Case 1 or case 2? B or D?
D.
D is going to be simpler?
I think so, yeah.
Okay. You'll, okay, this is fine. But later you'll find out that this case, case B, is going to be much simpler. And you'd like all T sections to be like this. I cannot compare case B to case C, just so you guys know, or between section A and B. Because section A happens when you have positive moment, section B happens when you have negative moment. But these two sections, B and D, they happen in the same location, right? Section AA, section AA. And the question is, when you do your analysis, where do you think the neutral axis is going to happen? It's going to happen within the flange, or it's going to happen below the flange? If it happens within the flange, this is great. Your life is going to be much easier when it comes to analysis. Now, we haven't seen the analysis yet, so you don't know. But we'll figure this out very soon. So, okay. Let me look here at the moment diagram and the tension. Now, what do you expect here in this location? I'm going to put here a box. What do you expect here? Positive moment or negative moment? Here's a column, and a beam. What is the expectation? Blake, can you help?
Positive.
Thank you. And how about here, Blake?
Is that negative?
This negative moment. So where do you need the reinforcing here? Is it in the top or the bottom of the beam?
Is that still
Yeah.
for me?
Yes, Blake.
I'm sorry, what was the question again?
Where do you need the main reinforcement, the tension reinforcement? Is it going to be top or bottom? It's going to be this guy or that guy?
Bottom, right?
No, in the negative
top.
moment. What does it mean by negative moment?
That it's.
Where's the tension?
Yeah, it's on the top. So you need, okay, on the top.
Okay. So here you need the tension reinforcement here. How about here? Where do you need the tension reinforcement? Top or bottom?
On the bottom.
On the bottom. Very good, Blake. So this is the reason that in here we splice the compression reinforcement. We splice here the compression reinforcement. We try to keep the tension reinforcement straight, intact. Because this is where you don't really need the reinforcement bar. So it's okay to start and stop. And your bar, same thing here. But here you'd like to keep it straight. It's going to be kind of a little bit tough to splice it. We call this a splice. What does it mean by splice? It means we just bring the two bars next to each other and that's it. They're not welded. You don't need to do anything. Just put them next to each other. That's it. Here is one slab, a picture for slab reinforcement. You just get a bunch of rebars, it's like a mesh. And of course, we time with this wire mesh just to keep them together, you know, when you pour the concrete. Some columns, we call this tied columns. Why tied columns? Because we have this ties. Look at this. This is what we call here a tie. There's going to be vertical rebars and ties. Some people also would call it stirrups, which is okay, but we just call it ties. Here are the column after they pour the concrete.
Dr. Najee, how do you know which one was positive and negative with the previous image?
Okay, all right, thank you. No problem. In here?
Yeah. Thank you.
Okay. Here's what happened, and of course, Blake can help me with this. I need here to think about the deformity shape of the beam. What's going to happen when you load it, right? You're going to be putting some loads here. Going to take you back here. What happened when you load the beam? The center of it is going to be coming down like the mid-span. So I'm going to be taking this here. I'm going to say, okay, it's going to be coming like this, right? I'm also exaggerating here when it comes to the amount of deflection, correct? But in here, no deflection is going to happen because the column. And then it's going to come like this and then deflect again like this. You agree?
Yeah. Yeah.
Okay, in a case like this, now where's the tension side? It's going to be at the bottom or the top?
At the bottom.
The bottom. We call this positive moment. How about here? Tension is going to be in the top, right?
Yes.
Okay, here it is. Negative moment, positive moment. You're good?
Yeah. Thank you. I appreciate
Okay,
it.
no problem there. So here's again the picture of the columns, and then now you understand the meaning of tight columns. You're going to have vertical rebars and then ties. You have another column that we call the spiral column. Why spiral? Because this guy here, like the tie, is not really like separate pieces. Give you one piece of rebar that goes around in a helical way. So we call this a spiral. Usually used in bridges, like what you see here. This is not a building. This is actually a bridge, right? Sometimes in big buildings or parking structure that you'd like to see this feature, like round columns. But most likely is going to be like in big bridges. You're going to see this column. So we call this spiral columns or round columns, if you like.
What are the advantages of that?
What's the what?
What are the advantages to a spiral versus?
Oh, the spiral
like
is okay. For the same material, for the same cross-section area of concrete, the spiral column is going to be stronger because you're going to have one piece of rebar that's really bringing the entire column together. So once you put pressure, it's going to be stronger. Also, when you look at this, the spacing between ties is going to be larger than the spacing between the spiral. So this is going to be like lots of horizontal reinforcements. It's going to be tying the column, right? So this column here is going to be stronger than this column. This is the main reason that we do round columns versus rectangular column. Besides, if the architect would like to see a round column, some people say, oh, it looks nice, you know, do you like it this way? So as a structural engineer, if they ask you and they say you would like to see round columns, you just give them some round columns, right? Because the architect is looking for this as an architectural feature.
I see, thank you.
No problem. Here's some footing. And as you see here, there's no form. See this? You just do a hole in the ground, put the reinforcing, then pour it in concrete. What's critical, you need to have enough concrete surrounding this reinforcing bars. And you see here's the footing. You have bottom mat, top mat, and then you have some vertical bars. These vertical bars, we call it dowels. Like in here, like in this case. Like this rebar is sticking above the column, we call this dowels. Like this piece here, we call this dowels, right? Some retaining walls, pictures of retaining walls, you know, it's like precast, prefabricated retaining wall. Now, bottom line, when it comes to any design, and this is what you need to understand, that you need to have more capacity than demand. I mean, this makes sense, right? What's the capacity? Capacity means how much force it can take. Right? This gives you the capacity or the strength. We call it strength or we call it capacity. Capacity is the same meaning as the strength of the structural member. And this capacity or strength, it can be in flexure, which means moment, capacity. It can be axial load, right? It can be shear, it can be torsion, it can be any of these forces that you learned about. So for each one of these, you're going to have a capacity and also you're going to have a demand. What is the demand? The demand is the force that you want your structural member to support. If you have given a beam and then you have some loads, you should be able to find out the moment demand on the beam. What's the moment demand? It's going to be that moment supported by the beam. This is how you want the beam to support, right? This is going to be the amount of force that, or amount of flexure force, which means bending moment that you want this beam to support. Same thing for axial load, same thing for shear. And you can do this for beams, for columns, for walls, for footing, it's the same. An axial load, we use the symbol of P. P is going to be for axial load. M is gonna be for what? Bending moment, which means flexion. V is gonna be for shear, right? And this T is gonna be for torque or torsion. So now understand, yeah, this says axial load, moment flexure, shear, and torque. So what is this PPN? What is P sub U? Which one is this? Which one is that, right? Which one here do you want to be larger? The capacity or the demand? Just asking you a hypothetical question, right?
The demand.
You want the demand to be larger or the capacity to be larger?
The capacity, because you want to be able to hold it.
Okay, so this give you the capacity, right? And P sub U is give you what? Let's say P sub U is give you the demand. So what's common between all of this? Between all of this, if you have one of these forces, axial load, moment, shear, and torque, if you put here sub U, it's going to be demand, which means ultimate. So ultimate is going to be used for demand. If you put here PPN, it means capacity. So all of this is going to be capacities, right? All of this. Correct? And all of this is going to be here a demand. Correct? Because it has this sub U. We call it demand. Sometimes we call it what? Ultimate. So the word demand or ultimate, you can use it safely. You can say this give you the ultimate force, or it's give you the demand force. Ultimate moment, demand moment. Ultimate shear, demand shear. How about the capacity? Do we have another name for it? Did I say something else?
The strength.
Strength. Thank you very much. Thank you. This is Angel, right?
No, that was Jasmine.
Oh, Jasmine. Okay. Thank you, Jasmine. Okay, good.
I was gonna ask, is serviceability another word?
Serviceability is something different that we're going to be talking about. Thank you.
Okay.
Thank you, Angel. Sorry. Okay, great. I'm happy that you guys are awake. You're listening. You're following up. Some good news. So basically, when you do any design, whether you do it in concrete, steel, or wood, or any other material, you need to be sure that you have capacity more than demand. Makes sense. And we call this strength design. So the method is a strength design. So, okay, now this makes sense. Here's definition of all of these variables. This phi is going to be a reduction factor. A reduction factor from what? Some safety. So this is going to be like some safety, right? After you find out the strength, let's say Pn, you need to multiply by some safety factor. So we call it strength reduction factor. How about Pn? Nominal strength for axial load. Mn, nominal strength for flexion. Yeah, for the moment, nominal strength. So Pn is going to be nominal axial load. What's nominal? It means nominal capacity, as it says here, nominal strength or nominal capacity. How about the ultimate, which is the same as the demand, is going to be ultimate axial load, ultimate moment, ultimate shear, ultimate torsion. Okay? You can say, okay, so I have two sides to balance. I have the demand and the capacity. Now let's work on the demand first. I guess you guys understand D means what? If I put here D, it means dead load. If I put L, it's going to be live load. And then you have some other loads that you may design for. But most likely in this course, I'm going to be doing dead load and live load only. Does this make sense? This is what I'm going to be doing. In the code itself, the CBC or the IBC, International Building Code, they give you some load combinations. They said, now forget about this F. F is going to be for what? For the fluid pressure if you have a water tank. So if there is no water tank, like just a beam, you just ignore this. Don't look at it. This is going to be 1.4 times D. Here is going to be 1.2 dead plus 1.6 live. Why? Because all the rest of these items, they don't have it. Don't have it in my beam, right? My beam analysis. So it's going to be 1.D plus 1.6 live. So it seems that I'm going to be taking these loads and multiplying by factors. I'm going to exaggerate the value a little bit. You see, look at this. Usually, this factor is more than 1. Why is that? Why would you like to increase the load a little bit? Why don't you just the load that's given? Someone's going to say, because I'm not sure. You consider, for example, for live load, you consider, let's say, for residential, I'm just going to throw here a number for you, it's going to be 14 pounds per square foot. For each square foot, you're gonna load it up to 40 pounds per square foot, right? And this give you like life load. Can you confirm that you cannot exceed this value? Can you confirm that no one's gonna bring a heavier furniture and use it there, or maybe someone's gonna have a party and bring more people inside his unit, his apartment? You cannot. Same thing for an office. This is a reason that you need to increase it a little bit for just in case. So this give you like the standard life load value for residential, right? And for office, let's say it's gonna be 50. So this gonna be for residential. And for business, it's gonna be 50 pounds per square foot. And then you need to multiply by 1.6. And for dead load, multiply by 1.2, add them together. Why would you do this? Because also the self weight of the stuff that you're gonna put there. Someone can put very light carpet. Another person is gonna put maybe heavy stone, for the flooring. So you need to account for that. How about the slab thickness? You know that you designed it to be 8-inch, but all of a sudden during construction they made it 9-inch or they made it 8.5. And you should be happy because your minimum is gonna be what? 8 inches. They give you more thickness, right? But at the same time, the thickness is gonna be increasing the weight. So you got to be careful. That's why we have this load factors. We call this what? This factors? Load factors. The 1.2, 1.4. And this method is called strength design method, which we are using here. And this is what we call here load combination. So let's say that I have dead load and life load only. What should I do? Gonna be taken here 1.4 times dead load. Compare it with 1.2 dead plus 1.6 life. Gonna be taken, the value is gonna be higher within the two. I can give you here a quick example. If I like here to put very simple numeric example. I'm gonna say dead load, let's say axial load equals 100 kips. Life load equals, which is just L, load equals, let's say 60 kips. Now I need your help. If I'd like to follow the first load combination, 1.4 dead, how much is this PU is going to be? So I'm going to say PU equals, I need help here,
140.
140 kips. How about pays on the second equation? 16.2 is going to be 1.2 dead plus 1.6 life. How much is that?
216.
216.
216 kips. So now I have two load combinations. Which one should I use in my design?
The smaller one?
216.
No, the bigger.
The larger capacity.
Yeah, so I'm going to say the larger. It is not capacity, it's going to be demand here. So the code says you need to use here the worst case. So the worst case for this load combination is when you add the dead load to life load with this load combinations. So I'm going to say this here controls my design, right? I'm going to say this just controls, and this is going to be the one I need to use in my design. This is how it works. Make sense?
Yes.
Especially when you have lots of other loads, like you have wind load, you have earthquake force, you have like snow, you have rain, you have earth pressure in the retaining wall, right? So you need to try all of these load combinations for all the load given and then pick the highest. And this is what the code says. With that, you have the demand. Now you know the demand on the beam, on the column, in terms of shear, axial load, moment, whatever, you name it. So this quick example, I did it only for axial load. And you can imagine that I can have this instead of PU, it can be M sub U. If I tell you here's the moment due to dead load, it's gonna be this much, and the moment due to life load is gonna be this much, so you can do your load combinations. So the difference is gonna be the unit. This is why it says here D. This D, it can be axial load, can be moment, can be shear, can be torque, can be anything. It's just like the applied load. It's gonna be the dead load, and whether it's gonna be axial, moment, or shear, doesn't matter. So okay. That was what? The demand. We're working here in P sub U. So we're done with this. We understand basically what is this about. Now, how about the phi factor, the reduction factor? You look at this. This is phi, phi, and phi, and phi, right? So are they all the same value? Like certain amount of reduction, and this reduction, is it more than one or less than one?
It's less than 1.
Okay, less than one, it's a reduction factor. Code here gives me this table and says when you have tension controlled section, like beams, most likely it's gonna be like beams, you take phi of 0.9. In what? Like in moment. So in moment, you use this, most likely. For axial load, you use this or this, depends on the spiral or the tight column or tight section. So it's gonna be 4 columns. How about for shear? It's gonna be this, and then you have some other values. So now we understand that the code is gonna give us certain guidelines and certain values that we can use when it comes to the phi factor, right? Good. How about this phi factor when it comes to this guy? Because I was not very clear on this. It says tension controlled section, but doesn't say beams. And here it says compression controlled sections, but doesn't say columns. So I'm gonna say, okay, it depends on, they give you this chart here. They say it depends on this phi factor, depends on the type of section that you have. For a spiral, you're gonna be following this dashed line and then it goes like this. For tight columns or tight beams, it's gonna be following this solid line. So okay, so why it changing? I mean, why the phi is changing? I'm gonna say because it's gonna be the amount of tensile strain that you're gonna have in the tension side of the beam. What's the tension strain? It means that I need to do some analysis and figure out the amount of strain that I have in the tension reinforcing bars, and based on this, I can figure out the phi factor. I'd like to do a quick example. The tensile strain at the bottom of the rebar, bottom rebar of the beam, was equal to 0.01. Where should I draw my line? I'm gonna say 0.01. It's gonna be here, right? Draw a section like this. Draw my line. Is this tight or spiral? I'm gonna say, yeah, this is like other. How much is the phi factor? It's gonna be 0.9. Another example. The amount of strain is 0.001. So my line is gonna be right here, correct? I have a rectangular section, so it has some ties. So I'm gonna be following this. So when the strain in the state is 0.001, the phi factor is 0.65. So there's a way of doing it. Don't consider that I covered this already now. No, we're going to be going in details, how to use this, what is the sloping line, and what is this, what is that, you know, we're going to be going in details about this. But what I'm trying to say is that this phi factor for these two items, right, is going to be based on the amount of tension strain that you're going to have in the bottom beam. Any questions? You can sign out if you want to. And you guys, you can have a good night.
Professor?
Yes.
How did, just a quick question. How did you want us to, do you want us to turn in the Excel file with homework 3, or how did you want it?
Absolutely, if you like to. Absolutely. Let me also look at it for you guys.
Okay, perfect. Thank you.
All right. You guys go ahead and sign out and you can go.
So
Thank
we
you,
can
Professor.
either
Thank you,
Excel
Professor.
or either on Excel or on paper, or would you
No,
prefer
at
on
the
Excel?
end, it can be on a paper, it can be typed if you like, but you need to show steps.
Okay.
So it is not this or that. It has to be typed, right? Or it's gonna be handwritten with all the steps, and also it's gonna be typed, it's gonna be also with the steps. So this is gonna be one thing, I mean, nothing else. Now, adding the spreadsheet to it is a plus. All right?
Regarding the exams, are we gonna be able to have like a formula sheet that we make,
Yes.
or yes?
No, I will make the formula sheet, I'll give it to you ahead of time.
Oh, okay, okay. That was the follow-up then. Thank you. Have a good weekend.
No problem. You too, guys. Good night.
Professor?
Yes.
When doing the like structural analysis, do they place does the structural engineer place the point loads such as like air conditioning units and stuff like that, like where
Yeah.
they actually go, or like worst case scenario in the center?
The worst case, but I mean, usually, yeah, they try to put in the worst case unless they know it. There's gonna be in this place, they can just do it in that place, you know. If
Yeah,
the
my
mechanical
only-
engineer has decided on it, then you just take it from him.
Got it. Like if it's already approved by the city, then there's no
Yeah, I
room.
mean, most likely no one's gonna change it, you know.
Yeah.
Okay,
And then cool. Thank you.
thank you.